Okay, so now I'm nervous. Okay.
No, don't worry.
No worries. So remember that on WebAssign, there is a homework set due today on 15.2. We're in the middle of 15.3. We'll actually finish that today. Actually, next Monday and Wednesday, I'm gone at a conference, but I'm going to record the 2 lectures ahead of time. Okay, so we're not going to skip any material, and I will upload those to the channel, but we won't meet in person on Monday and Wednesday. We'll reconvene a week from today. So Monday, Wednesday, we will not meet in person, but I will record the lectures and send you out some reminders to watch those to kind of keep up with things. I think that what I will end up covering in those 2 lectures is something called Green's theorem, which is an important application of some of the stuff that we've been doing. Okay. So don't forget to finish that homework set on 15.2 tonight. I will upload a new WebAssign assignment here pretty soon on 15.3 that will cover the fundamental theorem of line integrals. Okay, so remember last time, okay, any questions before we dive in here? Any questions? Okay, the fundamental theorem of line integrals, and you guys know how much disdain I have for the word line integrals. Okay, but what it basically says is that if you compute the work integral, remember there's a couple of different kinds of line integrals. There's so-called mass integral, which is a natural extension of the kind of area integrals we were doing in the past. Okay, there's mass integrals and there are work integrals. Okay, mass integrals involve densities or scalar functions at their core. And then if you look at line integrals that have a vector field acting on them, you can compute the work done by that vector field as you traverse the curve. And that's given by that special capital F dotted with dr work integral. Remember, we kind of talked about all of that. But the fundamental theorem of line integral says that the integral of a conservative vector field acting on a particle as it traverses the curve, okay, which that's always given by the gradient of some potential function dotted with dr, is equal to f evaluated at the end of C, minus f evaluated at the start of C, which means that the curve C itself doesn't matter. All that matters is its beginning and its end. Okay, that's amazing. That's an amazing thing. It says something interesting about how conservative vector fields actually behave. Okay, but let's actually think about why this happens to be true. Okay, so why is this true? Okay, I always hesitate to use the word proof in a calculus course, but we really are going to sort of give a proof for this because it's not very hard to do. Okay, we're going to argue why it is that this happens to be true. All right, so remember when we were doing the chain rule? Okay, remember when we were doing the chain rule? Okay, and we had, like, a function that depended on, x, y, and z or something, and then x, y, and z in turn might depend on something. Yes, in this case, we would tend to want to parametrize the curve C. Okay, we would say that C is parametrized by, r of t equal to x of t, y of t, z of t, where t travels from A to B. A equal to or less than t, equal to or less than b. Okay, now, if I replace x, y, and z by x of t, y of t, and z of t, then on the whole, x depends on t, y depends on t, and z depends on t. Don't you see? Yeah. And therefore, f itself will depend on like t alone. Does that make sense? Okay. Okay, so let me just kind of draw the little tree diagram that represents this thing. So f really in the end depends on t itself. Okay. So in other words, what would be the derivative? So suppose I wanted to take the derivative with respect to t of f with x replaced by x of t, with y replaced by y of t, and with z replaced by z of t. Okay. Well, right. Do you remember? What you do is you kind of go along each one of these branches and you figure out the cumulative change along each one of those branches. You would take the x derivative of f and multiply that by the derivative of x with respect to t. But of course, you need to evaluate the x derivative of f at x of t, y of t, z of t, okay? Now it's annoying to write x of t, y of t, z of t over and over and over again. So please permit me to just write that this is like r of t, don't you see? Yeah? Okay. Well, that means like if I just travel through this tree, that means that the derivative with respect to t of this is going to be the x derivative of f evaluated at r of t times what? What would I have to multiply by if I'm going along sort of the top part of this thing? I would have to multiply that by what? X prime of t, yeah? Okay. And then I would have to add in what we do along that middle branch, which would be the y derivative of f evaluated at r of t, okay, multiplied by y prime of t, okay? And then finally, we get a contribution of a rate of change along that bottom branch right there, which is going to be given by f sub z evaluated at r of t times z prime of t, yeah? Okay. So watch this. Watch this. This is going to be interesting. Okay, look, the integral over c of f dotted with dr, okay, if we just use our straight up, right? So by the way, f, why am I writing f? What should I really write? But it's not f in this, right? I actually know that f is given by the gradient of this thing, little f, yes? Okay. Which, by the way, is written another way, integral over c, this is just f sub x dx plus f sub y dy. Remember this alternative notation that we had, yes? Plus f sub z dz, which, by the way, if I plug all this stuff in, it's going to be the integral from a to b. F sub x, that needs to be evaluated at x of t, y of t, z of t, which is just r of t. So this is going to be f sub x of r of t. Okay. And what is dx? Well, dx is x prime of t dt. Yes? It's just x prime of t dt. So this is going to be times x prime of t. I'm going to factor out dt. Okay. So just so you know, I'm going to factor out dt from everything. Okay. And this is going to be plus f sub y of r of t times y prime of t plus f sub z of r of t times z prime of t. Okay, let me close off these parentheses. And all of this, I factor out the term dt. Okay, but what is this? What is all this junk right here that we just came up with? What is that really? Isn't that just the derivative with respect to t? Right, this is d dt of f evaluated at r of t, just by the chain rule. So, I mean, seriously, how do you compute that integral? Think about it. If that complicated junk is just the derivative with respect to t of that, this is literally like the derivative with respect to t of this thing, and you're saying, get the antiderivative of this derivative. So what are you going to do to compute that thing? What are you going to do? What's this going to be equal to? What is the antiderivative of the derivative of f of r of t?
F of R of T.
F of r of t. So it's going to be f of r of t evaluated between a and b. And lo and behold, this ends up being f of r of b minus f of r of a, which, by the way, is just another way of saying f evaluated where r of b, that's just the end of c, yes? That is the end of the curve. So this is little f evaluated at the end of c minus little f evaluated at the start of c. Okay? I think that's pretty cool, okay? What we just showed was, look, the chain rule actually tells us that that complicated mess is really just the derivative of that simple thing with respect to t. You just have to think it through. So we just verified that anytime you have a conservative vector field, i.e. there is a potential function so that the vector field is equal to the gradient of it, then the curve itself doesn't matter other than just the start and the end points. And you can compute this work integral by just computing the potential function at the end and subtract the potential function at the beginning. I think that's pretty remarkable, okay? I don't know, you guys don't seem too excited about it, but I am. I will not let you deter my my celebration, okay? My personal celebration. So here's like a little corollary, okay? Or corollary, if your name is Kevin Roper, okay? So let's see here. Corollary to the fundamental theorem of line integrals, okay? It's that the following are equivalent. The following are equivalent, okay? 1, vector field F is conservative. 2, F is equal to the gradient of little f for some potential function little f. Okay. 3, how can you tell that a vector field is conservative? We've talked about this. There is a particular concept we know. Yes.
The curl of the function is equal to 0.
Yeah. Curl of f, which, by the way, I would remind you is just del crossed with f, is equal to the 0 vector. Yes. Okay. We actually say i.e. capital F is irrotational. Okay. 4, the integral over c of f dotted with dr is, quote, independent of path, i.e. all that matters is what? Is where C starts and finishes, starts and ends. Okay. 4, or sorry, I already did 4. 5, the integral over C if C is closed. Remember, you write this little circle right here. That just means that C is closed, which means it starts and ends at the same place. So the integral f dot dr over any closed curve is going to be what? Yeah, equals 0. Okay. All of these things mean the same thing. Okay. If you start computing work integrals for a vector field over a particular curve that starts and ends somewhere, and you start realizing, holy mackerel, it doesn't seem how I go from the beginning to the end. I keep getting the same answer. You start to suspect that that thing is independent of path. So you start to suspect it's conservative. And the way you can check that is by computing its curl. And you're like, oh my goodness, yes, definitely a conservative vector field. Yes, okay. So the way you should think about a conservative vector field is that like it flows really kind of smoothly around, okay? There aren't any rotational tendencies anywhere. So there's no little, what we would call eddies or whirlpools anywhere in the vector field itself, okay? Things just flow along real smoothly. Okay, things like, and there are some very important forces in the universe that do this. For instance, gravity itself is a conservative force field. Okay, that's something that's fairly easy to check. If a vector field is like flowing kind of uniformly in one direction, even if it kind of goes like this and kind of ebbs and flows back and forth, that's going to tend to be a conservative vector field. The problem starts when the thing kind of starts going around in a circle or something like that. That tends to ruin stuff, okay? And by the way, sometimes it's even possible to focus locally in certain parts of the vector field, and those parts of the vector field will actually be conservative if we just hone in on that one part of the vector field. Okay, get away from all of the whirlpool parts or something like that, yeah? Okay. Any questions on that? Questions? By the way, we had another concept related to vector fields. Curl measures rotational tendencies at a point in the field, yes? And it gives us kind of the axis of rotation in accordance with the right-hand rule. And a longer vector field represents a more violent tendency to rotate about that point, yeah? A shorter one, it's like, okay, yeah, there's something going on here, but not as much as if it were longer. We also had, what's the other concept? Divergence, right? Which sort of measured the tendency of a vector field to be compressed or expanded at a point. That is losing material or gaining material at a point. And we talked about, why the formulas for those things actually made sense as well. But let's do some examples, shall we? Okay, any questions on this before we move on? Any questions? Okay. Let's do a couple of examples here. Notice, like I proved the fundamental theorem of line integrals for a 3-variable vector field, but seriously, I mean, that wasn't all that important. I could have had sort of a vector field on 2-dimensional space also, and the proof would have been exactly the same. Okay, so don't freak out if we look at a 2-dimensional thing and act like it's working the same. Okay, so compute this. Compute the integral over C of 2x minus 3y plus 1 dx plus, oops. I'm gonna stick to my notes here. Okay, minus 3x plus y minus 5 dy. So if C is the triangle with vertices 0, 0, 2, 3, and 4, 1. Okay. Okay. What do you think? Is this a conservative vector field or not? By the way, normally I would have to kind of specify. Here it matters the way that I go around this triangle. So here's a picture of this triangle right here. Let me just kind of draw it up here in the corner. Okay. So it's the triangle with vertices 0, 0, 2, 3, okay, and 4, 1. Okay, so normally, like, it sort of depends whether I'm going in the one direction or the other, okay? Because if I'm going in one direction, the vector field might actually be helping me. And if I go the opposite way, the vector field might actually be hurting me. Do you see what I'm saying here? That didn't matter for mass integrals. The direction of traversal on the curve did not matter. but it certainly matters for these work integrals. So here I also need to specify a direction around this curve. Let's just pretend that we're going in this direction like this. Okay, now, if we were to compute this thing directly by hand, what would I have to do to pull this off? What would I have to do to actually compute this if I were doing it directly by hand? Yeah, Paul.
Split it up into 3 separate curves and then parameter.
Yeah, that's right. And so I would have to do like, I might have to call this one C1, this one C2, and this one C3. Okay. And I might say like, okay, C is going to be like C1. You guys know what I'm doing, writing here. I mean, I'm using plus here, right? But you know what I mean. Yeah. C1 plus C2 plus C3. And you would say that the integral over C, which by the way is a closed integral, okay? Okay, that would be equal to the integral over C1 plus the integral over C2. I would compute the work done along C1, the work done along C2, add that in, and the work done along C3. Okay, so we would need three parametrizations. Parametrizations. Okay. Ugh. Right? It would be nicer if this thing were actually like a conservative vector field, because if it were, we wouldn't have to parametrize anything at all. We would immediately know this only depends on the beginning and end point, which by the way, for this collection of curves going around this triangle is just going to be the same. Start and the end are going to be the same. Okay. So is this conservative? That's something that you should get used to asking. Is the vector field conservative? Conservative. Is the vector field conservative? Well, here we have that f of x comma y is equal to 2x minus 3y plus 1, comma. Now be careful because there's this minus sign right here, don't you see? So I kind of have to distribute that to the second coordinate function right there. So the second coordinate function is going to be negative 3x minus y plus 5. Okay? And by the way, if I want to think about this vector field as living in three-dimensional space, I could also give a third coordinate function here, namely what? What would the third coordinate function be? 0, okay? Because when we compute curl, we really defined this for three-dimensional vector fields, but the way we get it to work in two-dimensional space is just by throwing in that third coordinate that's 0. Okay, if I compute the gradient, or if I compute del crossed with f, okay, so once again, how do we do this? This is like I, j, k. Okay, del is this crazy thing, partial x, partial y, partial z. Okay, and then I put in these things, 2x minus 3y plus 1. Okay, and then the second thing is negative 3x minus y plus 5, and then 0. Okay, I got to keep these things a little bit separated here, just so you can see them here. Okay. All right. Well, let's see here. Incidentally, since this vector field lives in two-dimensional space, doesn't it make sense that if there is a curl vector that it would point either straight up or straight down? Yeah. If there are swirling tendencies, you're going to get curl vectors, which are axes of rotation that are perpendicular to the xy plane, either pointing up or down. Therefore, you expect the x and y coordinates of this thing to be 0, okay? Which they will be. If you think about it, you cross out the first column and you go partial with respect to y. Okay, you cross out the first row and first column. You go the partial with respect to y of 0 minus the partial with respect to z of that junk. And hey, what do you get? 0. Okay. Then you cross out the second column in the first row. Okay, and you kind of do things backwards there. You're going to do the partial with respect to z of 2x minus 3y plus 1, which is 0, minus the partial with respect to x of 0, which is 0. Okay. And the only thing that's going to really be a, an interesting computation is the last one. Okay. So you go the partial with respect to x of negative 3x minus y plus 5. And what do you get? Partial with respect to x of that thing is negative 3. Okay. And then you go minus the partial with respect to y of the other thing, 2x minus 3y plus 1. So minus the partial with respect to y of that is plus what? Plus 3. Hey, what is this thing? 0, 0, 0. So is it conservative? Yes. Indeed. Indeed, it is conservative. So remember, if the thing is conservative, then there should be a way to kind of find a function f such that the x derivative is equal to that and the y derivative is equal to that. Who cares about the z derivative, right? I mean, who cares? Yeah. The z derivative being 0 just means that there aren't any z's in there. Yeah. There just literally aren't any z's at all. So really all you care about is that the x derivative equals that thing and that the y derivative equals the other thing. Now we've done these kinds of problems before, correct? Where you kind of go through and you integrate in x and then you integrate in y, etc. But a lot of times you can just eyeball this thing and figure out what has to be like an antiderivative. Okay, so for instance, if the x derivative of f is equal to that, what can you say? So think about this for a minute. Let me just circle this guy right here. If the x derivative is equal to that stuff, what does that tell you about f of x comma y? So think about it. F of x y equals, look, I'm taking that into account to figure out what f of x y, what the form of f of x y would have to equal. I would have to take the integral in x, correct? And what would I get? What's the antiderivative of 2x with respect to x? X squared. Okay, what about minus 3y? What in the world is that? Negative 3xy, yeah. And what about 1? If I do the antiderivative in x, what's that? Plus x. And then there's one little thing we have to worry about, because like here I am integrating, right? In this direction, I am integrating in x, yes? If I wanted to go back, I would take the partial with respect to, x, yes? And if I take the partial with respect to x of that thing, I could have stuff that only depends on y that would actually go away. So there is a little constant I have to add in here that depends only on what? A constant that depends only on y. And by the way, that could include numbers. Yes, like 5, right? So it could be 5y plus 3 or something like that. Yes? Okay. So we know that this is the form of f of xy. It's like x squared minus 3xy plus x. We know that our search for a potential function is not in vain because this is a conservative vector field. We have already verified that, yes? We know that we will be able to find a potential function. But let's stare at this guy right here. Let's stare at this second thing right here. We know that f sub y has to be equal to that. Okay, but working with this, let's see here. What's f sub y equal to? So f sub y equals, interestingly, f sub y would be equal to negative 3x. Ah, so far so good, right? Okay, there's the only other place that we could possibly have some y's is in c of y, don't you see? So it's going to be plus c prime of y. So what does that tell you? If you look at this thing over here, and this thing that we just came up with, what do you know that c prime of y has to equal? What does c prime of y have to equal? 5 minus y, negative y plus 5. It's got to be all that other junk. Okay, so negative y plus 5. Therefore, can't we figure out now what this thing has to be? So let's see, there would be x squared minus 3xy plus x, okay? Plus, okay, if the derivative of this thing that depends on y is negative y plus 5, then what is the original thing? I would have to just integrate with respect to y, don't you see? Yeah. So to kind of get this thing from this thing, I would integrate with respect to y. And so what do we get? What's the antiderivative of 5 if we integrated that with respect to y? 5y. Okay. What is the antiderivative of negative y? What's the antiderivative of negative y? Negative 1/2 y squared. Okay, so check it out. We've cooked it up so that this thing will exactly have x derivative equal to the x coordinate and y derivative equal to the y coordinate, correct? Yeah. So we have this thing. What is this thing? Here's what's kind of interesting, yes? For this particular thing, what will the integral be? Or what should it be? If we go around the entire triangle, what should the integral be?
0.
Yeah, should be 0, yes. Okay, but I actually want to work this out. So the integral over C, or the integral around C itself, the gradient of little f dotted with dr in this case is going to be 0. Okay. And it will be because we have this potential function right here, but here's what's kind of neat. They could give us any of these, like we could actually compute the integral along any one of these curves and get it very, very quickly. Okay, so for instance, what about the integral over C1 of the gradient of f dotted with dr? Well, let's see here. That would have to be f evaluated where I'm using the fundamental theorem of line integrals. Where would I need to evaluate f at? Integral over C1 would be f evaluated at 4,1. Okay. Minus f evaluated at what? 0, 0. Okay. Which, by the way, is equal to, okay, so what is that equal to? That would be equal to, so f of 4, 1, f of 0, 0 is easy enough to figure out. That's just 0. F of 4, 1, okay, would be 16 minus 12. Okay, 16 minus 12 is 4, plus 4 is 8. Okay, plus 5 is 13, minus a half. So it's like 12.5 or something like that. Okay, that's interesting, 12.5. Okay, and let's compute the other ones just so that we have peace of mind in terms of this thing working out. We know that if we compute all of these work integrals along each one of these curves, their sum total had better be what? 0. Okay, so let's do the second one here. What about the integral over C1, C2, the gradient of f dotted with dr? Well, that's going to be f of, okay, what was that? That was 2, 3, f of 2, 3 minus f of 4, 1. Okay, f of 4, 1 was 12.5. So now we just have to figure out what f of 2, 3 is. F of 2, 3, so 2 squared is 4. Okay, 2 times 3 is 6. So 4 minus, oh boy, okay, so 4 minus 3 times 2 times 3, which is, what is that, 18? 4 minus 18 is negative 14 plus 2. Okay, so 4 minus 18 is negative 14, plus 2 is negative 12. Okay, plus 15 is 3 minus 1/2 minus 9 halves. Okay, so what did I get? 3 minus 9 halves. What's 9 halves? Isn't that 4.5 or something like that? 3 minus 4.5 is negative 1.5. So negative 1.5, and then I have to subtract off 12.5 here. And what do we end up getting for this thing? So negative 1.5 minus 12.5 equals, what is that? Negative 14 or something, yeah? What about the integral over C3? Gradient of f dotted with dr. Let's see here. Well, that had better be, so that's going to be f of 0, 0 minus f of, what is it, 2, 3? Of course, we just computed 2, 3. F of 0, 0, that's easy. That's just 0. So it's 0 minus, okay, we just computed f of 2, 3. It was negative 1.5. So it's going to be plus 1.5. And of course, if you add all three of these things together, what do you get? 0. It had to be. Yes, it had to be. But the whole point here is we can compute all of these line integrals very quickly now that we have this potential function. In fact, someone could immediately just say, hey, here's this other path I want you to compute this work integral over. And we would, now that we have the potential, we can just instantly compute what the work integral is. And it doesn't even matter what the path is. By the way, it doesn't even matter that the path happened to be a triangle. It could have been some crazy thing that began and ended at the same point, yes? And then we still would have gotten 0 in the end, okay? All right, any questions on that? Questions? Okay, well, let's do one more here. Okay, so what about this? Let's do, so example, what about this? The integral over C f dotted with dr, where f is equal to 1 z y. So f is a vector field on three-dimensional space. And C is going to be parametrized by r of t equal to cos t, sine t, t squared, where 0 is equal to or less than t is equal to or less than pi. Just to make sure that we're all kind of remembering stuff that we've done in the past. What kind of a curve is that going to trace out? Look, x is cos t, y is sine t. What does that trace out if I just think about x and y? It's going to be a semicircle, yes? It's going to be the upper half of the semicircle traversed in the counterclockwise direction, yes? Okay. And then we have that t squared third coordinate. So all that's going to do is what?
It's gonna make it look like one of those barbers.
Yeah, it's going to look kind of like one of those spiral things or something, but you're only going to go up a little bit, yeah? Okay, it's going to go whoop like that. I won't attempt to draw that, but you kind of know what's going on here. So first of all, let's think about what the start of this thing is. So the start, of course, is r of 0, which is, okay, what is that? So the start is r of 0, which is 1, 0, 0. Yes? And the end of this thing is r of pi, which is, okay, interesting. If I plug in pi, cosine of pi is -1, right? Okay, sine of pi is still 0, and then the third coordinate is pi squared now. Okay, so we have the starting and the ending points. Now let me ask you a question. Is this thing conservative? Is this thing conservative? Okay, and what I'm trying to do is move us away from like having to check the curl necessarily. If this were conservative, you know that the first coordinate would have to be the x derivative of a potential. The second coordinate would have to be the y derivative. And the third coordinate would have to be the z derivative of a potential, right? So this would have to be little f sub x. This would have to be little f sub y. And this would have to be little f sub z. Now, you can go check the curl, but just sit here and think about it for a minute. Can you think of a function, little f of x, y, z, that has the property of having x, y, and z derivatives equal to those things? Yes.
X plus YZ.
X plus YZ. That simple. X plus YZ, don't you see, right? If you take the x derivative of that thing, you'll get 1. If you take the y derivative, you'll get z. And if you take the z derivative, you get y, yes? You kind of combine all of those steps and you think about, what's happening, okay? We could have gone through the same process that we've gone through in the past, but we have that thing. Therefore, this thing is conservative because we found a potential function. We could have checked the curl and checked that it was 0, but we have this thing. Okay, so in other words, this thing is equal to the integral over C, the gradient of this potential dotted with dr, which is going to be f of the end, little f of the end of C, minus little f of the start of C, which is f evaluated at, right, we already figured out what the end of C was. That was -1, 0, pi squared, minus little f evaluated at 1, 0, 0. Okay, let's think about this. X equal to -1. Look, the YZ part is going to be 0 every time for this starting and ending point, yes? So it's going to be -1 minus, minus what? Minus f evaluated at 1, 0, 0, which is just 1. So we get -2. Now, what does that mean? What does that mean in terms of whether how this vector field is behaving as we traverse this curve? If we were to look at this thing in three-dimensional space, we were to graph this vector field, and we were to graph this curve, and we kind of know what this thing is like. It's like a little half spiral staircase or something. Yes, it goes whoop, like that. What would the vectors, the vector fields themselves, look like relative to our traversal of that curve? Would they be flowing in our face, or would they be flowing with us? In our face. In our face, yes? That's why this thing ends up being negative. The dot products are over on the whole, from the beginning to end, mostly negative, yes? So that's why this thing ends up being -2. Any questions on that? Questions? Hopefully that kind of makes sense. Any questions? Yeah.
Just to clarify, the way you got your was just taking the partial of each one.
I just thought to myself, look, I want to have a function that has x derivative equal to 1, right? And you say to yourself, well, that means I need x, yes? But I also want to have a function that has y derivative equal to z and z derivative equal to y. Well, a y derivative equal to z and z derivative equal to y, you could just use yz. Does that make sense? So I have the x and I have the yz. What do I do with those to make it work out? Do I multiply them? No. If I multiply them, it's not going to work out because the x derivative would have been yz and not 1. So then what we did is we just added them together. By the way, do I need to add, like these potential functions, do I never ever need to add constants to them? No, because when I take the difference, what would happen to those constants? Just like in the fundamental theorem of calculus. Yeah, there it is. 15.3 is in the books.